Aluminum nitride has recently been a material of interest in piezoelectric micromachined ultrasonic transducers or PMUTs. PMUTs utilize a thin film of piezoelectric material which deforms when a voltage is applied to convert electrical signals into sound waves and vice versa, and find use in fingerprint sensors, gesture detection, and other devices. In order for aluminum nitride thin films to be of use in PMUTs, they must have good crystallinity. The nucleation and growth of crystals is a complex process that is dependent on temperature, as described by the equation for the nucleation rate. Similarly, surface diffusion of defects in a crystal is dependent on the temperature as described by the diffusion equation. The growth rate of crystals in diffusion generally increases with respect to temperature, as temperature is directly related to the kinetic energy of the particles. The temperature can be increased either during growth by substrate heating or after deposition by annealing. In this study, titled Spectral Analysis of AlN Growth at Elevated Temperatures, aluminum nitride thin films are grown on different substrates via reactive radiofrequency magnetron sputtering without substrate heating at low power and then annealed in a nitrogen atmosphere at various temperatures. The films are then characterized using various techniques. The XRD patterns and Raman spectra of the aluminum nitride films indicate that the as-grown films are amorphous, and even after annealing at higher temperatures they remain amorphous. Refractive indices calculated from UV-vis spectroscopy data of as-grown films are lower than literature values, likely due to volumetric defects such as pores and cracks. This is supported by optical images of the thin film showing that defects in the material consolidate into visible regions as the annealing temperature increases. More details will be discussed in my thesis defense.